All right, here we go. We're back at it. We're going to do the rest of section 1 of motion, forces, and energy. We are going to start on page 11. We did speed, so you're going to continue with where you were at speed. This should be I believe this is a capital C, is that right? So we're going to read about average speed. Average speed. If a sprinter ran the 100-meter dash in 10 seconds, she probably couldn't have run the entire race with a speed of 10 meters per second. Consider that when the race started, the sprinter wasn't moving. Then, as she started running, she moved faster and faster, which increased her speed. During the entire race, the sprinter's speed could have been different from instant to instant. However, the sprinter's motion for the entire race can be described by her average speed, which is 10 meters per second. Average speed is found by dividing the total distance traveled by the time taken. Okay, we have that. This is what we've been doing with our hopping and walking and finding the speed. An object in motion can change speeds many times as it speeds up or slows down. The speed of an object at one instant of time is the object's instantaneous speed. To understand the difference between average and instantaneous, think about walking to the library. If it takes you a half an hour to walk 2 kilometers to the library, your average speed is the distance divided by the time. 2 kilometers divided by 0.5 is 4 kilometers per hour. However, you might not have been moving at the same speed throughout the trip. At a crosswalk, your instantaneous speed might have been 0 because you're not moving. You're waiting for the traffic to stop. If you raced across the street, your speed might have been 7 kilometers per hour. If you were able to walk at a steady rate of 4 kilometers per hour during the entire trip, you would have moved at a constant speed. Average speed, instantaneous speed, and constant speed are illustrated in figure 4. Okay, we have a ball rolling, and notice our time is at equal intervals. 1, 2, 3, and 4 seconds. The ball is moving at a constant speed because the distance between each ball is the same. The distance traveled in each interval of time is the same. Now, what do you notice different about this ball? Okay, we have our time again is 0, 1, 2, 3, and 4 seconds, the time intervals, but what do you notice about the distance between the ball here and here? What is the ball doing? Tell me tomorrow. Okay, Christian, thank you. All right, so we have number 1, average speed is our heading. I'm only going to take 2 facts away from that. That average speed is the total distance divided by the time taken, and instantaneous speed equals the speed at an instant. It should be instant. All right? Very good, Abby. All right, now we're going to look at page 12, graphing motion. Okay, this is a blue heading. Therefore, this will be the next capital letter. Oh. All right, graphing motion. You can represent the motion of an object with a distance-time graph. For this type of graph, time is plotted on the horizontal axis and distance is plotted on the vertical axis. Figure 5 shows the motion of 2 students who walked across a classroom plotted on a distance-time graph. All right, so distance-time graphs and speed. A distance-time graph can be used to compare the speeds of objects. Look at the graph shown in figure 5. According to the graph, after 1 second, student A traveled 1 meter. Let's look at the graph. All right, after 1 second, student A, with this solid line, traveled 1 meter. Her average speed during the first second is the distance traveled divided by the time, which is 1 meter per second. Student B, however, traveled only a half a meter in the first second. So his average speed is a half a meter divided by 1 second. So student A's speed was faster. Student A traveled faster. Now compare the steepness of the lines. Okay, which of these lines, if you had to walk up this hill and this hill, which would be harder to walk up? That's the steeper line. That's the faster speed. All right, where are we? The line representing the motion of student A is steeper than the line for student B. A steeper line on the distance time graph represents a greater speed. A horizontal line on the distance time graph means that no change in position occurs. In that case, the speed represented by the line on the graph is 0. Okay, this is what we did in class in fourth period today, and we're going to do this in third period tomorrow. All right, we looked at that. So there's a lot to write down for this. All right, we have capital D because it's the fourth blue heading, red heading. What color is it? I don't remember. All right, and our topic, number 1, our red heading is distance, time, graphs, and speed. We're going to write down 5 things. You put the distance on the vertical axis, the Y. Time goes on the horizontal axis, which is the x-axis. Okay, distance time will compare the speed of an object. The steeper the line, the faster the speed. And if it's a flat line, there is no movement. Okay, that's a lot. Pause it. And when you're done, Bo, click play. All right, velocity. If you're hiking in the woods, it is important to know in which direction you should walk in order to get back to camp. You want to know not only your speed, but also the direction in which you're moving. The velocity of an object is the speed of the object and the direction of its motion. This is why a compass and a map, like the one shown in Figure 6, are useful to hikers. The map and the compass help the hikers determine what their velocity must be. Velocity has the same units as speed, but it includes the direction of motion. The velocity of an object can change if the object's speed changes, its direction of motion changes, or they both change. For example, suppose a car is traveling at a speed of 40 kilometers per hour north, turns left at an intersection, and continues on with a speed of 40 kilometers per hour. The speed of the car is constant at 40 kilometers per hour, but the velocity changes from 40 kilometers north to 40 kilometers per hour west. Why can you say the velocity of a car changes as it comes to a stop at an intersection? All right. So what's changing? If you come to a stop at an intersection, what is changing? Yep, that's right, Victoria. The speed is changing. Now, think about velocity when we have speed and direction. Remember back in the beginning we talked about distance and direction. What was that called? If you combine the distance traveled with the direction. What is that called? All right, there's our picture. Okay, you need to know the direction so you can get back to where you started. All right, capital letter E, velocity. We have 2 items we're taking away with us. Velocity is the speed plus the direction of travel. And there's 3 ways velocity will change. Velocity changes if the speed changes, the direction changes, or they both change. All right, thank you for visiting. Have a wonderful evening, Lucas. We'll see you tomorrow.